All right. Here we have a Rankine cycle. Okay. And it says a boiler of a Rankine cycle operates at 7,000 kPa, and then we have a condenser that's operating at 50 kPa. Usually, boilers and condensers are always isobaric. So, looking at this, we can say that this P1 is equal to P4 and P2 equals to P3. Okay. And at a turbine inlet, we have a temperature. So this is T3. The pump is isentropic, and then the isentropic efficiency of the turbine is 85%. And the pressure loses in the boilers or condenser are negligible. That's where we say we're assuming it's the same. And the water is leaving the condenser at being subcooled by 6.3. And then the boiler's size of mass flow of kilogram. So that's the m dot 220 kilogram per second. Okay, so first, what I would do is always like create a table. From that, we can fill in everything we know, and from that, we can go ahead. So state one, we know it's 50, okay, and then 7,000, 7,000. And for the isentropic ones, they change in temperature, but not in pressure. And we know that as soon as you have an isentropic efficiency, that means that that state that's going out of that, you're gonna have two of them. So for the pump, since it's isentropic, we don't have two S. We only have two actual. And this one, we can say that this is 50, and this is 50, all in kPa. And then we know that this is 550 degrees Celsius. And yes, so what I would start with is we can start with the enthalpy and entropy values for state 3. So we go to the property tables, and we look at oh my god, we go to A4 or A5. I'll go A5. And it says it's 7,000 kPa. And now at 7,000 kPa, it is much higher than 285. So you can't look at the saturated table. We have to go to this table. So 7,000 is just 7 megapascals. And from 7 megapascals, we look at 550. And here are your entropy and enthalpy values, these two. So we have 3531.6 and then 6.9507. Okay, so let's fill these out. And you have 3531.6. And then for the isentropic one, we know it's the same for this. So that's how we find our S4 value, S4S. Okay, then right here it's superheated, just to help us write it on the TS diagram later. Um, so for this, now we have 50 kPa, right? So we go back to this table and we go at 50. And we look at our enthalpy value, or entropy value, it is within range of these two. So that since they're within range, it gives me that it is saturated mixture. And then we can say that our temperature is 81.32, or we can say 81.32. So that's how much it's going out of the turbine. That's the temperature going out of the turbine. So um, from this, we can find a quality. So, and then from the quality, we can say that it's 6.905 minus 1.0912 over 6.5019. And that's going to give you a quality of 0.9012. Okay. And your HS, from the quality, we can multiply that by these values. So 2304.7 plus 340.54. So it's 2417.53. Okay, perfect. So now, now this is when we utilize the isentropic stuff or the isentropic efficiency. So from our energy balance, we know that the work of the turbine produces work out. Okay, so this is work out, and then this is Q in. This is a boiler, and then this is work in, and this is Q out. Okay, so from our energy balance, this is for at least the the pump, the turbine. So we have Q in minus Q out dot dot plus work in minus work out plus m dot of. I'm just not gonna write the kinetic and potential because we're ignoring that, and we know it's only one inlet, one outlet, so we're removing the summations, and we can say that it's H in, which is H3 minus H4. So crossing this, and it's steady, so crossing that. So we can say our work out equals to m dot of h h3, I mean, minus h4, but we're going to say h4s because this is a w out s. Okay, so we can say to find the efficiency, we know the efficiency is work out s. Since s is isentropic and it's your peak, you want the peak is producing the most amount of work out, but the actual is always less. So that's why it goes on the top and confirmed by your turbine. That's why your actual is above. So you're gonna have, let's do it. So we ignore the mass flow. We can say it's specific work out actual over work out S, which equals to 0.85 for your efficiency. That's just going to be H3 minus H4S over H3 minus H4. From that, we can solve for it. So H3 is 3, 5. Did I miss? Wait a minute. That should be 3,000. Yeah. Oh, okay. 3,000. Just, and that should fix it. So 3531.6 minus 2417.53 times 0.85, and then 3531.6 minus that. So our actual is going to be, just let me confirm my answer. Okay, it's not in the wrong. So it's 2584.64. Okay. From that, we can look at the range of 50 kPa over here. Is it within range or is it not? Okay, so it is within range. You don't need to find the quality, but you can say it's a mixture because that's going to help you to add it on your TS diagram. And we don't need our isentropic one. And we can say that the temperature also is 81.32. Okay, and we said that leaving the condenser, it is being subcooled by that. So it's Tsat minus T subcooled equals to the actual T. Okay, so it's 81.32 minus 6.3. I'm just going to round that and say it's 75. Okay. So from that, we can say that state 1, it's at 75. But since it's staying at the same amount of pressure at 50, our temperature right here, it's lower. So that means you are a compressed liquid. Okay, so we say it's compressed liquid. At the compressed liquid, we want to do a compressed liquid approximation. When doing a compressed liquid approximation, always go for the A4 table, the temperature table. So now we have this, okay? This is our entropy. because we're taking an approximation, so let's say it's 314.03, 314.03, and I don't think we need the entropy, okay? And we want to find the work in the pump now, because that's going to help us find the state too. So, work in the pump, we have to do a pump work approximation. So work in is going to be H2 minus H1 m dot, or we can just simplify this to say work in kilojoules per kilogram. From this, we can make this is just energy balance, like I just made it quick. Um, so pump work approximation, it says that you have your specific volume of the initial state, and then you get the differences in pressure. Okay. And that, so our specific volume at 75 is going to be the saturate. So it's this. So it's 0.001026. 0.1026. Let me just 0.001026. That's going to be 7,000 minus 50 equals to 7.1307. And now we add H1, so H2 equals to that. So H2, this plus that, equal to 321.1607. Okay, so from that, since it's a slight change in entropy and you can't find these values from the tables, we can just say that, or we can assume that the temperature coming out is just slightly above 75 or slightly equal to 75 because your entropy just barely changed and it's isentropic. So technically, uh, from your entropy, so we can see that's 1.58 point, and we know it's isentropic, so it's 1.58. It's still technically still in the compressed side because you're not moving much on the table. And okay, so compute the rate at which the heat is added to the boiler. So we want to find Q in, compute the power operating by the pump, and then so this is the power by the pump as kilojoules per kilogram, and Q in is just H3 minus H4. So Q in is H3 minus H2, which equals to 3531.6 minus 321.10.1607. Wait, I keep missing. Okay, equals to 3210.44 kilojoules per kilogram. Okay, and we have compute the power by the pump, return that. Or the power by the pump, they want it in kilowatts, usually power's in kilowatts. So just take that times 20, and that's going to be 142.614 kilowatts. And then we want to find, and then the rate for that, we also multiply that by 20. So that's going to be 64208.786 kilowatts. And then it says determine the net power produced by the cycle. So we want to find, we found work out. So work out is going to be h3 minus h4, so we have work out equals to h3 minus h4, and that's going to be, so it's 2584.64 equals to 946.96 kilojoules per kilogram times 20. It's going to be 18939.2 kilowatts. That's how much work out, and then work net out is the difference from those. So minus 142.614. So it's 8796.586 kilowatts. And then we want to find the efficiency, which is just Q net out, W net out over Q in, and that's going to be 6.4 divided by that, flipped. Or let me just do that better. To 29.27%. Let me check. Yep, that's correct. And for the TS diagram, just putting everything in. So we know that these are mixtures for state 4. So we can say 4 here, 4 here, this is for actual, 4S, and then 3 is superheated. So this is 3, this is 1 over here, and then we can just and say state 2 is here. And draw your isobars. Here's the first one. And then here is your other one. And then these are at 50. These are 7,000 kPa. Okay. And that's all for this question.